Thin shell structures are everywhere in the real world and have complex deformation behaviors. In physical simulation, to capture their mechanical response requires finely detailed, high-quality, and high-resolution meshes. But fine-resolution direct simulation is in general too slow to give interactive user feedback. While on the other hand, coarse-mesh simulations run fast but generate unacceptable artifacts and inaccuracies. The recently proposed progressive simulation framework offers a promising opportunity to bridge this gap with consistent and progressively improving simulation over a hierarchy of increasingly high-res models. However, a fundamental limitation to this first version of progressive simulation lies in its reliance on a hierarchy of meshes created through loop subdivision. That is to say, when generalizing to shell simulation with curved surfaces, an important aspect to note is this method restricts user input to a coarse shape without any surface details being added as it refines. Consequently, any surface that is not representable by repeated loop subdivision of a base mesh, either with complex boundary or intricate built-in details, just cannot be simulated. Meanwhile, the collision geometries will have to be a nested shape handled separately. To address all these limitations, we introduce progressive shell quasistatics (PSQ) to extend progressive simulation to support the high-fidelity modeling and design of all input shell geometries with unstructured triangle meshes. Given an arbitrary triangulated high-resolution model, our algorithm will first construct the hierarchy in a fine-to-coarse manner, and then correspondingly build a tailored prolongation operator specifically designed for shell simulation. For instance, in this balloon inflation example, the quasi-static simulation first runs as a coarse scale to provide the user with a preview. Once it converges, automatically refines all the way to the fineness level with fine-scale simulation details being progressively added, while the converged solution at each level remain consistent along the way. Meanwhile, we also propose a context-safe upsampling mechanism to enable safe spatial refinement under extremely large deformation and frictional contact. We first show a few unit tests that demonstrate PSQ captures important structural behaviors at the fine scale. In this example, a metal sheet is bent and sheared, while the coarse level previews remain consistent with the fineness level solution. Similarly, we show a half-dome stays stable as a symmetric equilibrium. Here we show a can crashing example where direct coarse level simulation exhibits severe locking artifacts, while our method produces an artifact-free coarse level preview solution at a comparable speed, and is predictive of the fine level convergence state. Compared to the prior work PCS, here is a zoom-in view to say clearly that because of sampling forces from a poor fine mesh triangulation and the suboptimal choice for prolongation, PCS generates errors and locking artifacts, while PSQ produces high-quality artifact-free results. In this twisting example, we see PCS coarse-level preview simulation yields overly creased spirals deferring itself from its final converged state, while our solution remains consistent and artifact-free. And compared to a fine prolongation, a fine fitting also incorrectly provides a volumetric approximation for shell deformation, hence generates poor force approximations during restriction, leading to jittering convergence, while our restriction operator smoothly diffuses the forces. In this scene, a metallic pumping character undergoes a dramatic compression, transferring from a rigid 3D form into a completely flattened thin sheet. Despite the extreme compression, PSQ can pause to compute consistent progressive simulation results for each level of refinement up to the final converged fineness scale solutions. Here we see an elastic bee toy engaging in the task of bubble blowing, which demonstrates a challenging case of turning a part of its body inside out. Here we inflate a balloon animal with 5 increasingly high-resolution meshes and show both the geometric and physical details being progressively added as it refines. It's important to observe that the application of our prolongation operator on a coarser level mesh independently generates a high-quality upsample simulation geometry. This feature proves useful for efficient preview even before the simulation converges at the fineness level. And finally, progressive simulation of some sleepy shell characters resting inside a rigid shape. Here both the collider and the balloon-like characters are modeled using unstructured meshes, which are simulated in one unified domain posed by an artist and then progressively refined. Thank you for watching.